Today we'll be solving an enthalpy problem. Our problem is, what mass of octane is completely burned during the heating of 20 liters of aqueous ethane 1,2-diol when it is heated from negative 10 degrees Celsius to 70 degrees Celsius? The volumetric heat capacity of ethane 1,2-diol is 3.7 kilojoules per liter degree Celsius. We'll start with the information we are given. The change in temperature can be calculated as 80 degrees Celsius. The volume of ethane 1,2-diol is 20 liters, and the volumetric heat capacity of ethane 1,2-diol is 3.7 kilojoules per liter degree Celsius. We'll start with the balanced combustion equation. Once our equation is balanced, we can use this formula to calculate the change in enthalpy by using the sum of the molar enthalpy of formation of the products and subtracting the sum of the molar enthalpy of formation of the reactants. To calculate the molar enthalpy of formation of a reactant, you take the molar ratio of a reactant and multiply it by its molar enthalpy of formation in kilojoules per mole. For octane, we'll take 2 moles and we'll multiply it by negative 250.1 kilojoules per mole to obtain negative 500.2 kilojoules. We'll do the same for oxygen and take 25 moles and multiply it by 0 kilojoules per mole because oxygen is an element. We can add those two values together to obtain the sum of the molar enthalpy of formation of the reactants and get negative 500.2 kilojoules. We'll now do the same with the products and take 16 moles of carbon dioxide gas and multiply it by negative 393.5 kilojoules per mole to obtain negative 6,296.0 kilojoules, and take 18 moles of water vapor and multiply it by its enthalpy of formation, which is negative 241.8 kilojoules per mole, to obtain negative 4,352.4 kilojoules. To get the sum of the molar enthalpy of formation of the products, we can add those values together to obtain negative 10,648.4 kilojoules. We can now use this formula to calculate the change in enthalpy, using the sum of the enthalpy of formation of the products and subtracting the sum of the molar enthalpy of formation of the reactants. We can use negative 10,648.4 kilojoules minus negative 500.2 kilojoules to obtain 10,148.2 kilojoules. This value is positive because we are calculating a change in enthalpy. Because we are trying to find the molar enthalpy of combustion of octane, we must divide it by 2 because 2 moles were combusted. When we divide this value by 2, we obtain the molar enthalpy of combustion of octane, which is 5,074.1 kilojoules per mole. Now we can calculate the mass of octane that was combusted. We can use this information we obtained from ethane 1,2-diol, which is a volume of 20 liters, a temperature change of 80 degrees Celsius, and a volumetric heat capacity of 3.7 kilojoules per liter degree Celsius. Then, we can calculate the molar mass of octane, which is 114.26 grams per mole of octane. And then we take the molar enthalpy of combustion of octane, which is 5,074.1 kilojoules per mole. We multiply all these values by each other. 20 times 80 times 3.7 times 114.26, but divide it by 574.1 kilojoules so every unit cancels out. Kilojoules and kilojoules, liters and liters, degrees Celsius and degrees Celsius, and moles and moles. Now we can calculate the answer of 133.3082123. We can round that to 133 grams of octane, or use scientific notation to obtain 1.3 times 10 to the 2 grams of octane. Good luck, Chem Stars!